Hello everybody, it's me, Code Trucker Ludo, signing in for another episode of the C Sharp Learning Series. And we have here with an amazing part of the chapter 2, which is the array. So we have covered a lot of arrays in the Python series and in the JavaScript series, but it doesn't hurt to look again on the arrays on the C Sharp series because it's a different language. So I'm pretty sure people who never saw my Python courses or JavaScript courses know what arrays are. So let's get into it. One-dimensional arrays. A one-dimensional array can be defined using the syntax data type variable name. Arrays can be initialized when they are declared if an array variable is not initialized, its value is null. You can specify the number of elements of the array when you initialize it. Or you can skip this and let the compiler infer it from the initialization expression. The following sample shows various ways of declaring and initializing arrays. Alright, in this example, array 1 and array 2 have the value null. Array 3 is an array of 6 integer elements all set to 0 because no initialization was provided. Array 4 and 5 and array 6 are arrays of 6 integers, all containing the same values. Once initialized, the size of the array cannot be changed. If you need to do so, you must either create a new array object or instead use a variable size container, such as a list T, which we'll look at in Chapter 7, Collections. You can access the element of the array using the indexer or with an enumerator. The following snippets are equivalent. Okay, this is shown in the following sample. Okay, although the effect of these two loops is the same, there's a subtle difference. Using an enumerator does not make it possible to modify the element of the array. Accessing the elements by their index using the index operator does provide right access to the element. Using an enumerator is possible because array types derive implicitly from the base type system.array, which implements IEnumerable and IEnumerable T. This is shown in the following example. Okay, in the first loop, we access the element of the array by their index and can modify them. However, in the second loop, an iterator is used, and this provides read-only access to the element. Trying to modify them produces a compile time error. Alright, here I need to create a new public void multi-dimensional array. Okay, a multi-dimensional array is an array with more than one dimension. It is also called a rectangular array. This can be, for instance, a two-dimensional array or a three-dimensional array, a cube. The maximum number of dimensions is 32. A two-dimensional array can be defined using the following syntax: data type, variable name. Multidimensional arrays are declared and initialized in a similar fashion with single-dimensional arrays. You can specify the rank, which is the number of elements of each dimension, or you can leave it to the compiler to infer it from an initialization expression. The following snippet shows different ways of declaring and initializing two-dimensional arrays. Okay. In this example, array 1 is initially null and then assigned a reference to an array of 2 rows and 3 columns. Similarly, array 2 is also null. On the other hand, array 3, array 4, and array 5 and array 6 are arrays of 2 rows and 3 columns. Array 3 has all of the elements set to 0, while the others are initialized with the specified values. The arrays in this example have the following form: 1, 2, 3, 4, 5, 6. You can retrieve the number of elements of each dimension using the getLength or getLength method. The first returns a 32-bit integer, the second a 64-bit integer. The following sample prints the content of the array 6 array to the console. see here. For integer I equals to 0, if I is less than array 6 that get length 0, then plus plus I. For integer j equals to 0, if j is less than array 6 get length 1, then plus plus I. Console writes, okay, arrays with more than 2 dimensions are created and handled in a similar way. The following example shows how to declare and initialize a 3-dimensional array of 4 times 3 times 2 elements. Or excellent, okay. Okay, I think we have to write this integer array 7 equals new integer 4 3 2 oh wow, this is kind of confusing. You know, let's do something cool. Copy. There. Okay. Okay, that's better. Another form of multidimensional arrays is the so-called checked array. We will learn about this next. Checked array. Void checked array Okay, checked arrays are arrays of arrays. These consist of other arrays, and each array inside a checked array can be of a different size. We can declare a two-dimensional checked array, for instance, using the syntax data type array variable name. The following snippet shows variables examples of declaring and initializing checked arrays. Okay. Okay. In this example, array number 1 and array number 2 are both set to null. On the other hand, array number 3 is an array of two arrays. Its first element is set to an array of 3 elements that are initialized with 0. Its second element is set to an array of 6 elements initialized from the provided values. The array 4 and array 5 arrays are equivalent, but array 5 uses the shorthand syntax for array initialization. Array number 6 mixes checked arrays with multidimensional arrays. It is an array of 2 arrays, the first one being a 2-dimensional array of 2 by 2 and the second a 2-dimensional array of 2 by 3 elements. The elements of a checked array can be accessed using the array ij syntax. This example is for 2-dimensional arrays. The following snippet shows how to print the content of the array 5 and array shown earlier. Okay, let me first now that we have looked at the type of arrays we can use in C#, let's move to another important topic, which is conversion between various data types. Okay, we reach another example. We reach another, section of the chapter 2. So let's get going. I'm gonna make another, another C# program for this section, and I'll be right back. All right, type conversion. Sometimes we need to convert one data type into another, and that is where type conversion comes in picture. Type conversion can be classified into several categories: implicit type conversion, explicit type conversion, user-defined conversions, and conversions with helper classes. Okay, let's explore these in detail. Implicit type conversion for built-in numeric types. When we assign the value of a variable to one of another data type, implicit type conversion occurs if both types are compatible and the range of destination type is more than that of the source type. For example, integer and float are compatible types, therefore we can assign an integer variable to a variable of its float type. Similarly, the double type is large enough to hold values from any other numerical type, including long and float, as shown in the following example. Integer I equals 10. Let's see here. Let's arrange void for so much stamping that you guys I don't see anything. I'm just writing like what I'm seeing here. I'm also studying this, okay? So integer I is equals to 10, float f is equals to I, long L is equals to the biggest number, and double D is equals to 1. The following table shows the implicit type conversion between numeric type in C#. Let's see this more. Come on. You can take a snippet of this. I will love you guys have it for your computer. Source type: short byte, char, short, u short, integer, u integer, long, u long, and float. Oh my goodness. Okay. There are several things to note about implicit numeric conversions. You can convert any integral type to any floating point type. There is no implicit conversion to the char, byte, and s-byte types. There is no implicit conversion from double and decimal. This includes no implicit conversion from decimal to double or float. For reference types, the implicit conversion is always possible between a class and one of its direct or indirect base classes or interfaces. Here's an example with an implicit conversion from string to object. String to object. Okay. All right. Now we're gonna make another explicit Okay, so when an implicit conversion between two types is not possible because there's a risk of losing information, such as while assigning the value of a 32-bit integer to a 16-bit integer, explicit type conversion is necessary. Explicit type conversion is also called a cast. To perform a casting, we need to specify the target data type in parentheses in front of the source variable. For example, double and integer are incompatible types. Consequently, we need to do an explicit type conversion between them. In the following example, we assign double value to an integer using explicit type conversions. However, while doing this conversion, the fractional part of the double variable will be truncated. Hence, the value of I will be 12. Okay. The following table shows the list of predefined explicit conversions between numeric type in C#. There you go. Please, you can make any snippet about this as well. I'm gonna go back in 3, 2, 1. Okay. There are several things to note about explicit numeric conversions. An explicit conversion may result in precision loss or in throwing an exception such as overflow exception. In converting from an integral type to another integral type, the result depends on the so-called checked context, and may result either in a successful conversion, which may discard the extra most significant byte, or in an overflow exception. When you convert a floating point type to an integral type, the value is rounded towards 0 to the nearest integral value. The operation may, however, also result in an overflow exception. C# statements can execute either in a checked or unchecked context, which is controlled by either with the checked and unchecked keyword, or with the compiler option checked. When none of these are specified, the context is considered unchecked for non-constant expressions. For constant expressions, which can be evaluated at compile time, the default context is always checked. In a checked context, overflow checking is enabled for integral type arithmetic, operations, and conversions. In an unchecked context, these checks are suppressed. When overflow checking is enabled and overflow occurs, the runtime throws a system.overflowed exception. For reference types, an explicit cast is required when you want to convert from a base class or interface into a derived class. The following example shows a cast from an object to a string value. The conversion from string into object is performed implicitly. However, the opposite requires an explicit conversion in the string. User-defined type conversions. A user-defined conversion can define an implicit or explicit conversion, or both, from any type into another. The type that defines these conversions must be either the source or the target type. To do so, you must use the operator keyword followed by implicit or explicit. The following example shows a type called fancy integer, which defines implicit and explicit conversions from and to integer. Public read-only struct fancy. You Tack. Sí, puedes tener. What to do? There is an error here, right? I do have. I'm trying to see something here, guys. Somewhere. All right, we just came back. I don't know what happened, but you're gonna see that I'm gonna have a huge this entire section here, this entire method here, it's gonna be inside a comment section. So you're gonna see a comment section in the GitHub project. Okay, so you can use this tab as follows. Fancy integer is gonna be second sample. Fancy integer new fancy integer. Okay, I think I'm gonna use a sample again here. It's gonna be this, and then it's gonna be this. Then copy this like this. Okay. In this example, a is an object of the fancy integer type. The value of a can be implicitly converted into integer because an implicit conversion operator is defined. However, the conversion from integer to fancy integer is defined as explicit. Therefore, a cast is necessary as in fancy integer I. Okay. Conversions with helper classes. Conversion with helper classes or method is useful to convert between incompatible types, such as a between string and integer or a system date time object. There are various helper classes provided by the framework, such as the system.bit converter, class, system convert, class, and the parse and try parse methods of the built-in numeric types. However, you can provide your own classes and methods to convert between any types. The following listing shows several examples of conversion using helper classes. Alright, let's copy this. Create here. Sample, just like so. It is important to note the key difference between parse and try parse. The former tries to perform a parsing, and if that succeeds, it returns the parse value, but if it fails, it throws an exception. The latter does not throw an exception, but returns Boolean, indicating the success or failure, and sets the second out parameter to the parsed value if successful, or to the default value if it fails. And with that, we'll reach the operators. And with that being said, we are done with this course, with this part of the course. So, thank you very much, guys. It's almost the mark, 25-minute mark. And if you enjoyed this course, please click like and subscribe. There's going to be more. We are still in chapter 2. So there's a lot to cover in each chapter. Of course, you can expect this class every week, every Tuesday of every week. And yeah, pretty excited about C#. C# is very, very powerful. And of course, because we're doing the game design course as well, after both are concluded, we're going to approach the Unity 3D engine with C#. So without further ado, guys, that'll be actually. I'm hoping that we can get this by the end of the year, but I don't think so. That must be a 2025 project. Just kidding. But yeah, that'll be mostly in 2025. So thank you very much, guys, and see you guys next time. Bye bye.